Alright, welcome back to another AQA A-level chemistry video. Today I'm going to be going through the general properties of transition metals, as well as breaking down the biggest misconception that's taught at GCSE as to what transition metals actually are. I'll be going through what transition metals are and also telling you the properties of transition metals. I'll be going through what the properties of a water metal is, as well as explaining what the extra properties that transition metals have over just normal metals. But yeah, I'm going to go, without further ado, I'm going to go straight into the video. So the transition metals have a set of properties which are characteristic of them. Now, I'm going to go break this down quickly, right? So one of the things that is true, and I'd say this, that in GCSE you're taught something that's not really true about transition metals. And they're taught to you because they're taught to you in that way because not because they're just trying to hide something from you. I actually praise GCSE for teaching it in that way because it wouldn't make so much sense for you guys to understand what transition metal is if they taught you the full truth of the way that transition metals actually are, because you haven't gained the right information for you to understand what transition metals are by GCSE. But by A level, you have already now learned enough information for it to now be able to make sense when I explain to you what transition metal actually is. So first of all, I'm going to break through the basic thing about transition metals, and it is true that they are in this area here. That is true. So that's not like a lie or anything like that. It is the full truth that transition metals are in this area here. But I'm not going to call them just this area here. We already know from I already done a video on this about the blocks, right? But we know that this area here is specifically called the D block. Why is it called the D block? Well, the periodic table is arranged in the structure of the atoms. Whether we're talking about the mass number, the number of protons, nuclear number, the relative mass of an atom, or the structure of the electrons, right? In this case here, when we're talking about which blocks we're talking about here, we're talking about the structure of the electrons. Now for A level, we know a bit more advanced than the 288 rule. We know about the orbitals. We know about the s orbital, the p orbital, the d orbital, and the f orbital. And you'd know that the elements are arranged, or the blocks are together because the final electron of that atom is found in that particular orbital. So if we're talking about the s orbital here, we know that all elements in this area here are called the s block because the final electron of these elements here are found in the s orbital. Also, and they're usually the alkali earth metals and the alkali metals, right? Also, hydrogen is also part of the s orbital. The reason why in most places they're separated out is because it doesn't follow that general trend that you always think. So why is hydrogen always separated out? It's because it doesn't follow that trend of the s orbitals being alkali earth metals or alkali metals, because hydrogen isn't a metal, it's a gas. It's not a metal, but technically it's in the s block because its final electron is its only electron is in the s orbital. And the same thing applies to when we're talking about the p block, where the final electron is found in the p orbital. Now you're probably thinking to yourself, actually no, let me just finish with the last one as well. No, actually, you're probably thinking to yourself, why the hell am I mentioning all this about the p orbitals and the d orbitals? If I wanted to get a video about how to find the orbitals, I'd go to another video. I don't see how that's relevant to this video. I promise you there is a reason as to why I'm explaining this. And obviously the last one here is being the f block. Now I'm not going to go spend too much time talking about the f block because in A level chemistry you don't actually need to know too much about the f block or f orbitals really. You just know that they're there. You don't need to know anything about lanthanides or actinides. I always thought you'd learn about them in A level. I was really curious about them. I think you'd know about it in physics, but yeah, you don't need to know about them. They may ask a very basic question on them, but it's based on the information that you guys already know. So you don't have to worry anything about studying about F block, right? Don't have to worry about them at all. The thing that you guys need to know is the S, P, and D. Now I said to you, there is a reason why I'm explaining you guys this information, because you probably just think yourself, why am I talking about this? Because when I'm talking about the one that we're going to focus on when we're talking about transition metals is the D block, right? Forget about the P and the S block. The one that we're actually going to be focusing on when we're talking about transition metals is the D block here. Now the misconception that is taught is that, so the truth is, yes, transition metals are usually found in this area here, right? That is true. But the misconception is that a D block element is a transition metal. That isn't true. A transition metal is a D block element. That is true. But that doesn't necessarily mean that a D block element is a transition metal. There is a difference between the two. And the difference is just this next part here, right? It's not even this. The definition of what a transition metal isn't that. It's just the title of this here. There's this little subtitle. That is the technical definition of what a transition metal is, right? A transition metal is an element. Again, if you want to know what the answer to it, they may ask a 1-mark question for this, and all you have to say is this: if they ever ask what define what transition metal is, it's just an element that has a partially filled d subshell or partially filled d orbital. That is it. That's all it is. It's just an element that has a partially filled d subshell or d orbital. And the biggest misconception is that the biggest thing that we need to get across is that transition metals aren't just metals in the D block. So the final triad of the D block, and I think there are more, but the ones that I definitely know for certain, again, I'm taking this information from Seneca Learning, so if you're screaming, notice there's more examples of D block elements that aren't transition metals, but this is just the ones that we need to know from here, right? Zinc, cadmium, and mercury aren't classified as transition metals. Why? It's because they have a full D subshell. They don't have a partially filled D subshell. So if I give, that's the main thing, right? That's the main thing they need to know about transition metals, that they have a partially filled D subshell. So I'm gonna go down. Let's just get some random D subshells here, right? I think D subshells have 10 electrons. So I'm gonna go 2 or 5. So 1, 2, 3, and then 4 and 5, right? I'll do another one here as well. 1, 2, 3, and then 4 and 5. And I'm gonna finish these off. So I'm doing the box. You should guys know about the box method when in terms of the box method in terms of how we represent the electrons in orbitals. So the boxes represent the orbitals, and the arrows would represent the half arrows represent the electrons in those orbitals. All right, so I'm going to do 2 orbitals here, right? Technically, I've done it in the incorrect manner. It's usually done like this. We usually write them like that, and then we go about. Again, I'm just doing this for the sake of an example, right? So I gave you these 2 examples here. What's the first thing going through your head when you're talking about transition metals? Are both of them do we have any transition metals here? Are both of them transition metals? Are none of them transition metals? Is one of them transition metal? You know, also what's going on here? And break it down simply, there's only one transition metal here. And the transition metal here is this one. This is not a transition metal. Why? Because it has a fully filled D subshell, and therefore it cannot classify as a transition metal. Whereas this example here has a partially filled D subshell, and it classifies as a transition metal. Now you're probably thinking in your head, why is it so important that a transition metal has a partially filled D subshell? Why is it so important that it's partially filled? What's the problem with it being a fully filled D subshell as opposed to being a partially filled D subshell? And that's because we're relating here to the properties of a transition metal. You guys know that, I don't know what you guys know about transition metals, but you should know that transition metals have properties that are different to the other metals. They have the basic properties of a metal, but transition metals have properties, even more properties than a standard metal, that make them so specific, makes them so useful compared to the other metals. Particularly in society, of course, all elements have their own specific properties, like the desirable traits. But when we're talking about transition metals in comparison to the rest of the metals, they have specific properties that are very, very unique. And when the reason for those properties are chemical. When you have a partially filled D subshell, you're able to enable yourself to have undergo certain chemical reactions or certain properties that you wouldn't be able to get if you had a fully filled D subshell. Now I'm not going to go too much into that. I'll probably go into that in my next video, but in terms of just explaining it here, transition metals share the properties, and these properties come about because of a partially filled D subshell, as I said here. But I'm going to go through what the standard, so what all metals have, right? I'm going to go through the properties of what all metals have, every metal that you guys know, right? And you should know this from GCSE as being hard. You know, metals are usually hard. The majority of the metals are hard, right? Obviously mercury is an example where it's technically not, because it's a liquid at room temperature, and the alkali metals, some of them are kind of easy to cut open or malleable, right? But you know, generally most metals are hard. Sonorous, most metals are sonorous, but again, you don't need to know that for AQA, because I think other examples, they other exam boards, they look for you to say sonorous, but I don't think you have to really say it for AQA level chemistry. But the ones you should know are that they're hard, shiny, and above all else, everyone knows that they are good electrical and thermal conductors. Now that's the properties of all metals. What what separates transition metals from the rest of the other metals properties, they have additional properties on top of the properties that you'd expect from a metal, and that they are generally the ionic properties, right? So I want to make it very, very clear when I say this, right, is that it's the ions of these metals that are the ones that have these properties. So the ions of transition metals have properties that are not shared by other metals, right? It's when we think about the transition metal, we're usually thinking about the ions of these transition metals, not just the standard transition metal as it is by itself. It's usually the ions of these transition metals that present the properties that we're really looking for here. It as an element usually is just kind of like any other metal. It's the ion that we usually care about, right? And the biggest difference that we're talking about when we talk about well, there's a few, but I think the one that's usually sort of a lot in industry is this one here. That they have multiple oxidation states. Transition metal. Oh, I don't know why I came up. Transition. One of the biggest things of transition metals is that they have multiple oxidation states. And I think one of the best examples that you guys will learn about is vanadium. Vanadium has quite a few oxidation states, but you get the rest with chromium and copper. You'll learn about quite a few did I say yeah, I already said chromium. There's multiple oxidation states, and that's what makes them so iron as well, and that's what makes them so useful, because they have multiple oxidations. But why is having multiple oxidation states useful? Well, one of the biggest reasons as to why having multiple oxidation states is so useful is actually for the third reason. I'll go on to the second reason, right? One of the biggest reasons as to why multiple oxidation states is useful is because it's useful as a catalyst. That is what catalysis is, the reaction of catalyst, right? Catalysis, right? And the reason why catalysts are able to act in the way they do, or what a catalytic reaction is just the chain reactions happening at different oxidation states. So when you have different oxidation states, you're able to undergo certain types of reactions where it may have a lower activation energy, right? Or again, you're having multiple reactions that have an overall lower activation energy than the reaction if it was happen in an uncatalyzed process. And that's because that metal was able to undergo multiple oxidation states to allow for the reaction to occur under a lower activation energy. Now, one of the biggest things and that's so useful in industry. Obviously, you can think of catalytic converters. Look how many things that require catalysts, right? Catalytic converters, multiple catalyzed reactions in industry. But one of the biggest catalytic reactions that you're not really thinking of is that most of these medicines that you take have transition metals in them. Think of iron. These tablets have iron in them. Now the iron is so useful because obviously iron is useful for obviously hemoglobin. People have some people have a low iron concentration, but iron in itself can undergo those catalytic reactions in your body that you may need to do, right? And that's what we think there's multiple catalytic reactions. And the reason why I say this is because in your exam you may have a 6-mark question, or maybe I think it's a 6-mark question, or maybe even slightly more, and don't get freaked too much about this, but you should know this by now. If you're listening to this video by the time it comes out, and it's an essay styled question, and not when I mean essay, don't think of like some long think they have to structure it really well. But they may ask a question as to why transition metals are useful in the industry, and explain why they're able to undergo that process. And one of the things you could talk about is catalytic reactions because of multiple, and explaining the reasons because of multiple oxidation states. And if you could be talking about certain properties, why it's useful in the industry, and as I've just given you an example, right? But that's why I'm just saying this out here, because I'm just thinking of things that are useful to your actual exam. I don't think it's useful just telling you this useful property, this useful property, because it's not relevant to, it may not be relevant to your exam. This particular point here is very, very relevant, and so I wanted to highlight that point very, very much. But the next part I wanted to focus on was the second point, and is they form colored ions in solution. I think most of you know that, but probably thinking so far, lots of pretty colors. Why is that so useful? There's actually, I forgot the name of the reaction. I'm actually gonna search up right now. I forgot the name of the. You know what? Doesn't matter right now. But there's a the reason why that's so important that certain transition metals form colored ions in solution is because we're able to calculate or detect using a certain apparatus. I forgot the name of the apparatus. It's really annoying me now. But we're able to detect or actually use a scale and measure the light intensity of a certain type of ion. And again, I'm not going to go through it right here, right now, but if we measure a certain concentration or certain light intensity, we know that we have a particular type of transition metal in our in that solution, right? We usually get a solution, we standardize it with a already known sample of something, right? Of already known sample of our solution. And if we have a certain light intensity that we measure from our solution, we know that we have a particular transition metal in our solution. And that's very, very useful if we don't know if we're trying to investigate what transition metals that we have in our solution and we don't know. And we can also use that information alongside a equation that you guys will learn a bit later to actually help us work out the concentration of our transition metal in our solution using the light intensity apparatus that again I've completely forgotten about. But if we know the light intensity, we can actually use that information to help us work out the concentration of transition metals in our solution, which could be very, very, very helpful for us. And now the last one, which is the most new to you guys and probably listening to this for the first time. Hopefully you're not listening to this for the first time if you're listening to this on the 7th of May, given that your exam is on the 12th of June. But hopefully you're listening to this, you're someone that's new, learning about transition metals for the first time a bit earlier than that. And that's something called ligands and complexes. So one of the properties of transition metals is that they form something called complex ions, and they react together with something called ligands. So complex ions are formed with ligands, and it's also something that probably doesn't make too much sense to you. And I'll explain what that means just next, right? I'll go through complex ions and the majority of these different properties in later videos, but I'm going to give you just a brief breakdown of what a ligand is. So first of all, this is what a complex ion looks like, right? Again, don't get confused by these little things here. That's just what you'd expect them to be, where this is the 3D object, right? So we have to show them as being a 3D, the wedge lines, the dashed lines. But again, and this is just a skeletal formula, so this is just CH2CH2 and then the NH2NH2 here, right? It's just diaminoethane. This ligand here, this would be called the ligand. It's just one of those, and this is called a diaminoethane ligand. But again, there's multiple ligands. I'm just going to go for what a ligand actually is. A ligand is just a molecule which forms a dative bond with a transition metal. So a dative, and if you don't, a dative bond can also be called a coordinate bonds in some books. I usually call them coordinate bonds. Sometimes I call them dative bonds, but they're the same thing. A coordinate bond is just where a lone pair of electrons is donated from one atom to another. But both electrons are donated from one atom, right? So the ligand donates a lone pair to the transition metal ion, and in this case it would be from the nitrogen, and it's the lone pair on the nitrogen atoms from this ligand are fully donated. So yeah, they're fully donated from the ligand to the transition metal here, right? and an ion with ligand attached to it is called a complex ion. So if in this case we have actually a chromate ion, and the chromate ion in itself, oh sorry, the chromate ion in this case, I don't know what I haven't got a specific one. Okay, it's called chromium 2 plus, right? But the chromate ion in itself is just as it is. But when it reacts with ligands by doing these dative covalent bonds, it's now becoming a complex ion, and we define the coordinate number. We call the coordinate number, or the coordination number, is the number of ions, as the number of the dative bonds between the metal ion and its ligand. So in this case, with this complex ion, to break it down very simply, the coordination number is just the number of bonds between the ion, the transition metal ion, and the and the ligand. The number of ligands is separate. There's 3 ligands here because these are all one. I said this is one ligand, and then I've just done it 3 times because chromium can actually form 3. This is chromium, right? I'm not just moving mad, right? Yeah, it's chromium. I'm not moving mad. It can form 3, but the coordination number is just the number of those dative bonds. So in this case, there's 1, 2, 3, 4, 5, 6. That's 6 dative covalent bonds. Therefore, we say we could describe this complex ion as having a coordination number of 6. And that's it. And that's all. That's the basics understanding of what I was trying to get back that example. Anyway, I couldn't. I was trying to find an example for this one here. Anyway, this is the basic understanding of general properties of transition metals, and that is it. So hopefully this video was helpful.